Hello and welcome back to lecture number 10 on our series on classical mechanics. So in today's lecture, we continue our discussion on central forces. So this is part 4. So up until now, we have worked on the second order differential equation. So we have the second derivative of u with respect to theta plus u equals to negative m over L squared u squared times f of u. So this is a differential equation is going to help us find the equation of the orbit if we are provided with an information about the central force. So that means if f of u is known, then what we can do using this differential equation, we can obtain the solution u, which will be a function of theta, and since we assume that u is equals to 1 over r, so we have r equals to r as a function of theta. So this will be the equation of orbit which we can derive from this particular differential equation. Another way of looking at it is like if we are provided with the information about the orbit, then we can use it as a solution to this differential equation, and that can be also used to determine the force or what type of force we have. So what we'll try to do in today's lecture, we'll consider a very special type of force, and using that particular value of force, we'll try to understand what kind of orbit the particle undergoes, which is undergoing that special type of force. So this special type of central force is going to be referred to as the inverse square law. Inverse square law generally means like if we have a force which is a central force in nature, so that means it's a function of r, so that will be given by negative k, where k is a constant of proportionality, divided by r squared. So this is the inverse square law. There are usually two types of forces that follows the inverse square law. One is the gravitational force and the other one is the Coulomb's electrostatic force. So let's use this particular force equation and we'll substitute this into a differential equation, and we'll try to study what kind of orbit or what kind of path this particle is traveling. Let's do that. So here we have the central force, which is given by f of r equals to negative k over r squared. So what we will do, we will use r equals to 1 over u, such that we have f now represented as a function of u, which will be equals to negative k u squared. So we'll use this force equation and we will substitute into our differential equation, which is the second derivative of u with respect to theta plus u equals to negative m over L squared u squared. So now instead of f of u, we have negative k u squared. Immediately we can see the u squared and the u squared gets cancelled out. So we have d squared u over d theta squared plus u equals to, so negative times negative will be positive, we have mk over L squared. So we will be only considering mass, which is constant. We'll not consider variable mass here. So m times k is already a constant, and L, the angular momentum, which is a conserved quantity, is also a constant. So we see here that this particular value on the right hand side is a constant. So let's bring it to the left hand side. So we have d squared u over d theta squared plus u minus mk over L squared equals to 0. Now what we are going to do, we're going to assume that this value u minus mk over L squared, let this be equals to, let u minus mk over L squared, let this be equals to u bar. Then if we differentiate both sides with respect to theta, then du over d theta, that's this second term will be 0. So this will be simply equals to du bar over d theta. Then if we again differentiate with respect to theta, so we have d squared over d theta squared, so that will be d squared u bar over d theta squared. So we'll use this to substitute in our differential equation, such that this particular differential equation will now become, let me write it as d squared u bar divided by d theta squared plus, so we have u minus mk over L squared, so that's simply u bar equals to 0. Now the whole idea of making this substitution is because now this particular differential equation thus has a very similar look to that of d square x over dt squared plus omega squared x equals to 0. So this particular differential equation represents the simple harmonic motion. Her solution is given by x equals to a times cosine of omega t plus theta. So if we compare our differential equation with the differential equation for a simple harmonic motion, then our solution will be something of the form. So we'll have u bar is equals to some constant a times cosine of theta minus theta naught. So here theta, now instead of omega t we've used here theta because our actual original differential equation, which is this one, is independent of time, so it's a function of theta. So instead of omega t we are replacing with it theta. Fine. So this is a solution to a differential equation. So let's further understand this. So we started out with this differential equation and we substitute the force with the central force with negative k u squared, which is the inverse square law, and then we obtained this particular differential equation, which is very much similar to the differential equation represented by simple harmonic motion, and that yielded the solution u bar equals a cosine theta minus theta naught. Now we assumed that the value of u bar, so that's u minus mk over l squared, so that's equals to a times cosine of theta minus theta naught. So u will be equals to mk over l squared plus a times cosine of theta minus theta naught. Now since u is equals to 1 over r, so we have 1 over r equals to, now what we'll take mk over l squared as the common factor. So I have mk divided by l squared. So if we take this as the common factor, so we have 1 plus we have a l squared divided by mk times cosine of theta minus theta naught. Right. Then we are going to consider, let l squared over m squared, let this be equals to l, and a l squared over mk, let this be equals to epsilon. This will be defining in a moment. This is known as eccentricity. We'll come to that. So this is now our equation. Now it's transformed into 1 over r equals to 1 over l multiplied to 1 plus epsilon times cosine of theta minus theta naught. And if we represent this equation in terms of r, so r will be simply equals to l divided by 1 plus epsilon times cosine of theta minus theta naught. Now this is a very special type of equation. So here what we have done, we have obtained the equation of the orbit r, which is written in terms of which is a function of theta, r of theta. So this is given by this particular equation. Now this equation actually represents a conic section. So what we'll do right now is we are going to stop for a moment here, and we're going to take a slight mathematical detour, and we'll study about conic sections first. We'll try to understand from where this particular equation arises and what are the consequences of the different parameters, and then we'll use that knowledge and come back again to this particular equation to study this equation of orbit. To define a conic section, we will need two things. One is a fixed straight line and a fixed point. So using this, we can define a conic section. A conic section is the locus of a point P, which moves in a plane such that its distance from a fixed point, we'll call this fixed point as S, it always bears a constant ratio to its distance from a fixed line. So this is the fixed line. So this fixed line has a name. It's called the directrix, and this fixed point is the focus. So let's use a schematic to understand this. So we start with a straight line that will be the directrix, and we have a fixed point. So this fixed point will be named S. So this will be referred to as the focus. And then we have a point. This is the point P, and this point P is going to move along the plane that contains the focus and the directrix in such a way such that we define the distance between point P and point S, and also define the distance of point P from the directrix. So the ratio of this distance is always going to be fixed. So let's name it. So let's say this line PS is making an angle theta with the, let's call it x-axis for the time being, and the fixed distances R. So the coordinate of this point P will be simply R comma theta. The perpendicular distance of point P from the directrix is D, and it meets the directrix at M. Now from the definition of the conic section, the ratio of the distance PS over PM, so that's going to be a constant, and it has a name. It's called the eccentricity. In our case, so our eccentricity E will be, so PS, that's the distance R, divided by PM. So PM is going to be distance D. Now let us suppose that the perpendicular distance of the focus S from the directrix is given by uppercase D, and let's say it meets the directrix at point O, such that we have OS equals to distance D. Fine. Now we will try to trace the path or the trajectory of this point P, or we can say the locus of this point P. Let's say for simplicity purpose, the particle is following a trajectory that resembles a parabolic path, and P is a point on this trajectory. Now we'll need to define another parameter L. For that, we will draw another straight line that passes through the focus and is parallel to the directrix, such that this distance S, we'll call this M prime. So this distance is L. So that means if we consider the point M prime, so you can say at point M prime, so what will be this eccentricity? So our eccentricity E will be, which is PS actually, so now it will become SM prime, divided by the perpendicular distance of point M prime from the directrix, which in another way is equivalent to SO, that is the uppercase D. So that means this will be equals to L over D. So what we have done is we have defined the eccentricity for theta equals to 90 degree, let this be equation 2, and another for theta less than 90 degree, which we label as equation number 1. Now if we consider the length uppercase D, so that comprises of this particular portion, which will be R cosine theta plus PM, which is D, right? So this is D equals to R cosine theta plus D. Next what we do is use equation number 1 and 2 and substitute it in D equals to R cosine theta plus D to get, so instead of D we can have L over the eccentricity E equals to, let's keep R cosine theta the way it is, plus we have small distance D, so D will be R over eccentricity E. Now we'll take R over E, the common factor from the two terms on the right hand side, so we have R over E, so that will become E cosine of theta plus 1. I can see that the E and E gets cancelled, and this gives us R equals to L divided by 1 plus the eccentricity E times cosine theta. So here we can see, so there's R, which is the coordinate of the point, or the coordinate of the point here r, which is the coordinate of the locus of the point P. So this is given by this particular expression, which represents a conic section. We derive the expression r equals to L divided by 1 plus epsilon cosine of theta. Here L represents the latus rectum and epsilon is the eccentricity of the conic section. Now this particular sign, which is positive in our case, could be negative, and that depends on what kind of origin of coordinate system we have chosen. In order to prove Kepler's 3 laws of planetary motion, we will need to consider a system in which a particle moves in an elliptical path whenever we have a central force, given by f of r equals to negative k over r squared. Under the influence of such a central force, we have a system in which an object moves along an elliptical path. For this, we need to be familiar with different parameters involved in an ellipse. So today's section is going to be based on understanding the ellipse and their parameters. And these parameters are going to be very useful in deriving the Kepler's 3 laws of planetary motion. So here we have an ellipse. So let's define the axis. So we have the x-axis and the y-axis. Then we are going to choose, so since it's an ellipse, it's going to have 2 foci. So let's call it f1 and f2. For this particular problem, we are going to choose our origin at focus f1. Now with respect to this particular origin, let's say we have a particle at point P. So we need 2 parameters to define its position. One will be the radius, that means how much distance it's away from f1, and with what angle it is with respect to the x-axis. If we choose our origin at f2 instead of f1, then in the formula of the conic section, we have 1 minus epsilon cosine theta in the denominator. Now with respect to this particular diagram, let's define L. So we will begin by drawing a straight line, which is going to be parallel to the y-axis. Actually, it's parallel to the directrix, and this particular straight line is going to pass through our focus f1. We name it, let's name it as RS. So the length of this RS, this is referred to as the latus rectum, and it has a length of 2L. So that means L here represents the semi-latus rectum. So here epsilon, or sometimes is represented by E, this is the eccentricity. So we will later show that the eccentricity of an ellipse, it's going to lie between 0 and 1. Now for different values of E, we get different conic sections. So let me note it down here as well. So if we have E equals to 0, when the eccentricity is 0, what we get is a circle. If we get the eccentricity to be exactly equals to 1, we have a parabola. And when the eccentricity is greater than n, then we have a hyperbola. So for our particular discussion today, so we will stick with the value of E lying between 0 and 1, and we will show that why this is the case. Okay, let's define 2 more parameters. So let's say this particular point is A, and this is B, and here we have C and D. So we have AB. So this AB is referred to as the major axis, and we will be denoting with the value 2 times A. So if we only consider A, so that will be the semi-major axis. Then we have CD. So CD will be the minor axis. So the minor axis will be 2B. Right. So this length is 2A, and this particular length is 2B. So our next task will be to find the value of the semi-major axis A and the semi-minor axis B. So for this particular ellipse, if we consider the origin to be centered at focus F1, then let's say this is a point P, then the coordinate of this particular point P will be given by the radial distance r and how much angle it makes with the positive x-axis. So this will be r comma theta. And if the origin is considered at focus f2, then from this center or from this origin, it can be determined with r prime and theta prime. The coordinate of that same point P will be given by r prime comma theta prime. So we have f1 P, so this distance is given by r, and f2p, so this distance is given by r prime. Right. Now we'll take a very specialized case. So let's take a case when the point P coincides. So let's call this as A, and this is B, this will be C, and this will be D. Point P coincides with the point A. Now, if that happens, then we can straight away say that f1p plus f2p, that's r plus r prime. So what we have done, we have taken 1 and 2 and added them to each other. Fine. Now here, since our P is coinciding with point A, so instead of f1p, we'll have to rewrite it as f1a plus f2a, and this will be still equals to r plus r prime. So that is how we have defined the coordinate of our point P. The whole reason for writing it this particular fashion is because of the symmetry of the focus. So here f1a is exactly equals to f2b. So that means in place of f1a, we can write f2b plus f2a. So this will be equals to r plus r prime. Now what is f2b plus f2a? So that is actually ab. So that means we can say that ab, let me write it here, ab is equals to r plus r prime. And we know that the value of AB, so that's the length of the major axis, so this will be 2a. So let's box it and label it as equation number 3. We'll be using it in a moment. So this particular equation is going to be a very general relation because it's going to hold for any point on this elliptical path, meaning we started out by assuming that the point P is at A, or it's coinciding with point A. It could be anywhere. It could be at point C, it could be at point B, or anywhere on the elliptical path. So this relation is always going to be true. That is, the sum of the distances of the point P measured from the two foci is always going to be a constant with value equal to the length of the major axis. So what we'll do next is we'll now shift the point B in such a way that it coincides with point C. So let's do that. So our point P will be now coinciding with point C. So if we measure this point C from our focus f1, so this will be R, and the same point P, which is actually C when measured from focus f2, so that will be R prime. Now here R will be equals to R prime. That's because of the symmetry of the diagram which we have chosen in such a way that these two triangles are congruent to each other, which means that f1c will be equals to R and f2c that will be equals to R prime. And if we add both of them, so we have f1c plus f2c, so this will be equals to R plus R prime. So here we will choose, because of the symmetry of this particular problem, we chose that f1c is equals to f2c. So this implies f1c plus f1c. So instead of f2c, we have used f1c. So that's equals to R plus R prime. And R plus R prime from equation number 3 was twice A. So we use this from equation number 3. So this will be 2 times f1c, which is equals to 2a, and this gives us f1c equals to a, and since f1c is r, so here we'll say that r value is equals to a. So this is equation number 4. So let me note down what we have derived so far. So we have obtained r plus r prime, so that's equals to 2a, and then we obtained the value of r is equals to a. So we'll use it. Now for the time being, let's assume that our point P is now again at point A. So in that case, we can say we can use our formula for the conic section. So R will be L over 1 plus epsilon times cosine theta. So theta, so that means when we have the point P coinciding with point A, so theta will be equals to 0. So we have cosine of 0 degree, and this will give us essentially the value of f1a. So that's simply L divided by 1 plus epsilon. Then if this particular point P now instead of at point A is coinciding with point B, then using the same formula, so here we can say that f1b this time will be equals to L divided by 1 plus epsilon. So the cosine of angle, now this angle will be this particular angle, which is 180 degrees. Let's call it pi. So that means we have L divided by 1 minus epsilon. So this is f1b. Now let's add both of them. So we have f1a plus f1b. So we have this length added to this particular length. So that will be L divided by 1 plus epsilon plus L divided by 1 minus epsilon. Now what is f1a plus f1b? So that's the length of the major axis. So this is 2a. So that means we have 2a. So that will be equals to, so we add these two terms. So we get 2L divided by 1 minus epsilon squared. So we have a equals to L divided by 1 minus epsilon squared. And we'll be using this as well. And if we solve for L, so that will be simply a times 1 minus epsilon squared. So we'll label this as equation number, let's call it 6, and this will be equation number 5. So now that we have an expression for the semi-latus rectum L, equation number 6, we'll substitute this value here and here. So this will give us the value of f1a and f1b in terms of a. So let's do that. So we have f1a, so that's equals to L over 1 plus epsilon. So L is a times 1 minus epsilon squared divided by 1 plus epsilon. So this will be a times 1 minus epsilon. And f1b, so that will be a times 1 minus epsilon square divided by 1 minus epsilon. So we'll get a times 1 plus epsilon. So let's label this as equation number 7 and equation number 8. Now let's determine the value of OF1. From figure, we can say that this value OF1, that equals to the semi-major axis OA minus F1A. So the semi-major axis, that's simply A minus A times 1 minus epsilon, and this is going to give us A times epsilon. So this is the length of OF1, which means this is the distance of the focus F1 from the center of the ellipse O. By symmetry, OF2, so this will be also equals to OF2, A epsilon. Next, what we'll do, we'll try to find out the value of OC. So OC, that's simply, we can use the Pythagoras theorem, that's the square root of the hypotenuse, which is CF1 squared minus OF1 squared. So CF1 we have already obtained, so this is R. So in place of R, we'll have A squared minus OF1 squared. So this is A epsilon. So we have A epsilon squared. Further simplification gives us A times square root of 1 minus epsilon squared. Now what is OC? OC is actually CD over 2. That's half of CD, we can say. This is the value of OC. And what is CD? CD is the length of the minor axis, which is 2b. So CD, which is the minor axis with a length of 2b. So that means half of CD will be simply b. So we have also obtained the value of the parameter b in terms of a. So that's a times 1 minus epsilon squared. Now clearly we can see the value of epsilon. For b to be a valid number, the value of epsilon must lie between 0 and 1. So this is the reason why the epsilon value for an ellipse is between 0 and 1. So let's summarize everything that we have obtained in this particular session. So we have an ellipse. So here we considered a point P, which is at a distance of r from the focus f1 and making an angle theta with the x-axis. Also the same point, when it is measured from focus f2, it's at a radial distance of r prime and making an angle of theta prime with x-axis. So we obtain that this is going to be true for any point in the ellipse, r plus r prime, that's always equals to the length of the major axis. So this is one case. Then we have this particular length, which is the length of the focus, or simply it's let me write it down, then I'll OF1. So this will be equals to a times epsilon, where epsilon is the eccentricity and the coordinate of this particular point f1. So that's simply a epsilon comma 0. Right. So we have here a. So a here is given by L divided by 1 minus epsilon squared, and b will be a times square root of 1 minus epsilon squared. So we'll be using those parameters a, b to derive the Kepler's 3 laws of planetary motion.